Hello everyone. My name is Afia Rasool and I am a PhD student in Smart Lab from University of Alberta. And the topic of my talk is computer vision based automated timber structural defect detection framework. The other authors of this work are Dr. Qipei and Dr. Rafiq Ahmad, who are the professors at the University of Alberta and also my co-supervisors. So as we all know that timber is a major substrate for the residential and commercial buildings all over the world and is suitable for panels, planks, ridges, beams, trusses. And like every other wood category, timber exhibits some of the defects. Majorly, if we categorize them into two categories, it would be the surface defect and the structural defects. Now, if you just go and look at the top right of the picture, it is these are the examples of surface defects, which are the knots and you can say the cracks. And this kind of defects occur at the very early stages of the manufacturing and can easily be, identified. But there are other defects like structural defects as you can see on the bottom, which are the bends and twists. So they are the defects which usually occur on the later stages of processing and during the drying phases of the stud timbers. So the motivation of this work is coming from an industrial scenario in which laborers actually do the thing manually, that they use different angles and their prior knowledge to identify the structural defects. So this is time consuming and also very inaccurate. So if we talk about the literature, there are quite a number of papers working on the computer vision size for the surface defects, but for the structural defect, there is little to no information provided. So the objective of the study is to generate an industrialized solution for precise localization of the defective timber by using a CV, which is fast so that it can be done on the real time. And also to do that, we have to generate our own data sets as there are no publicly data sets available for the structural defects of the timber studs. So here is an overview of the methodology that we have adopted. So it starts with the dataset preparation, of course. So we collected the data with different camera angles and the stud sides, and then we did some of the data cleaning that involves the noise removal, format convergence, and resizings. And then we did the manual annotations using the label image tool. And right now, the defect classes are only one, which is defect, and we categorize it as the structural defects. And then after the dataset preparation is done, we split the dataset into four different categories, which is train, validate, test, and then predict. And I have used different variants of YOLO V8, which are available to get the best accuracy and to study like the accuracies between the variants. And once the model training is done, we did the model predictions, and these predictions can be used for real-time decision automation. And also, if we want to go back and want to improve the initial setup, it is very important. I will explain how. So the dataset preparation starts with the initial setup. We use the both sides of the stud, which is the face and edge, because the structural defects are quite bit tricky because the bends and the twists can be seen from one side but cannot be seen from the other side. In the same way, they can be seen from some angles but cannot be seen from the other angles. So and also that is why we use different angles of the camera and different heights, which is 2 feet, 6 feet, and 18 feet to get different dimensionalities. And the overall, we for the initial work, we only got to study 15 studs in total, with 3 studs which were taken into the data set as the non-defective studs and the other as the defective studs. So after the resizing, cleaning, and the annotations, we got around 350 images of 640 by 640, and that we split in the form of a 65% for the training, 15% for the validation and testing each, and 5% for the predictions. Oh yeah. So on the right side are some of the instances that are taken from our developed data set. And as you can see that some of the defects are very evident from the top, but some of are very evident from the side view. So for the model training, we have used YOLO V8, which is a single stage detection model using the CSP.NET as the backbone, and for the multi-scale feature extraction, because as I said that we have multiple images, multiple different defect sizes. And then for the neck, it is path aggression native based fusion of these multi-scales. And then the head actually classifies these defects and give the bounding boxes and their scores. So the idea of using YOLO V8 here was that because it is very lightweight and fast and can be used for a real-time predictions, and also because it supports multi-scale feature extractions. Again, on the right side are some of the properties and their values that we used during the time of the training. For example, the machine specifications, the software versions, and also the training parameters. So, and also we have to keep this thing in mind that when in the real time, when we are taking the pictures of the stud for the identification of the defect, the lighting effects can differ. So that's why for the before the training purposes, we did some of the dataset augmentation to play with the hues and the lighting effects of the images to make it more robust. So the evaluation matrices for this study was the Bayesian recall and mean average Bayesian. And as I said earlier, that I have used all of the available variants of the YOLO V8, which is nano, small, medium, large, and extra large, with different number of layers, different number of training parameters, and speed. And as you can see from the this table, the validation and testing Bayesian and recall for these modules is different when applied on the same dataset. And with the slightly better accuracy with YOLO V8 medium. Some of the observations can be seen from the model training and model inference quantitative results. So the top two graphs are basically the mean average precision 50 and mean average precision 50 to 95 for the bounding boxes versus the number of epochs. And as we can see that these YOLO V8 variants can achieve between 75% for the mean average precision of 50 and between 40% for the mean average precision of 50 to 95. And then the graph C is basically taken from the training. So this is the training precision versus epochs. And as we can see that all of the variants are actually converging between 100 to 200 epochs, which is a very optimum time. And then the last graph is about the validation and inference mean average precision. So at the time of the validation and testing, the mean average precision 50 was around 75%, and the mean average precision 50 to 95 was around 45%. So all of these specifications let us know that we tried our best to not the model be overfit or underfit, provided the fact that our dataset was quite small and also the defects was quite tough. So based on the quantitative results, we chose YOLO V8 medium trained weights for the model predictions, and these are the results of the model predictions that we got. And an important thing that we can notice from this insight is that the 2 feet angles are the most optimum one for the real-time application, because the accuracy is maximum here and it starts to gradually decrease as we move the camera forward. But still, the combination of the forward, like the farther and the closer views are the optimum choice. So to conclude, I would say that by applying the YOLO V8 and generating a small data set, which is quite tricky, we achieved around 75% of the testing accuracy for the prediction of structural defects. So this research is very important in a sense if we want to mitigate the waste and we want to eliminate the waste, because right now what's happening in the industry is that of course there is a time wastage and also there is a material wastage when they see that the study is not usable. So what we can do further to extend this work is to utilize the defective non-defective part for some of the reasons. And also, we are extending this work to enhance the data set based on the insights that we got, and also to enhance the algorithms. And yeah, this is all about my presentation. I would like to have any questions that you have.